Hello there, Precalculus students. Now, the other day, some of us got to where we were graphing this system and solving it on the calculator during class. Others of us did not get there. So take a look at it with me if you didn't see it. If you did go through and learn how to do this, then you may bypass this portion of the video. Now, I want to remind you that we know how to do this problem already. Let's review, okay? So I'm going to go ahead and draw a coordinate plane because we can do every bit of this by hand. And I want to review that because anything we can do to help you review is a good thing. So the graph that I'm going to do in red, do you recall, is a quadratic function. It forms a parabola that is right side up. I see that it moves right 1 and down 5. So right 1 and down 5. Now, I see that its A value is 1, and since its A value is 1, that means from the vertex, I count out 1, up 1 on both directions. So there is my parabola. And of course, my second function, which I could do in blue, is just a linear function. I see that it has a y-intercept of 0, 3. And then I'm going to count down to, try that again, right 1. And that's going to give me my line. So just a quick review of what you already know. I also want to remind you that when I talk about solutions of systems, I'm talking about where the graphs would intersect each other. It is completely doable to solve this system by hand, but I want to practice it on the calculator. So take a moment, pause the video if you need to. Put that on your calculator. You will see that I have those two equations on my calculator, and let me hit zoom 6 so that I can graph them. So that's what I expected it to look like. Now, finding the solutions on a calculator it's quite easy, and it's faster than solving equations. If we go to our almighty calculate menu, all right, remember when you have two graphs on the same coordinate plane, your up and down arrow keys become active. They cause you to toggle between the two different graphs. But what I need to do to find an intersection is simply move the cursor to where it looks like it's on the intersection. So you don't have to have as much precision when you're using the intersect command. So go to your second calculate, your calculate menu. We want choice 5, which is to find the intersection. For first curve and second curve and guess, just hit enter. So you hit enter 3 times, and I can see if I am rounding to 3 or 4 decimal places, it would be appropriate to say the point of intersection is 2.646, comma, negative 2.292. So again, 2.646, comma, negative 2.292. You can also round to 4 decimal places. So finding the other intersection is equally easy. I'm going to start tracing to the other intersection. As long as your eyeball close, it's good enough. You don't have to be as precise instead of left bound, right bound. So I can't get much closer than that, but still going to my calculate menu, hitting intersect, hitting enter 1, 2, and 3 times. I get my intersection is negative 2.6.6, comma, 8.292. So negative 2.646, comma, 8.292. The decimal portions of each answer are consistent because what you're working with is a plus or minus the square root of situation if we were to have solved it by hand. So I'm getting the same decimal approximation. Now, to review on finding maxes and mins, this comes back to yesterday's lesson. If I enter this second equation on my calculator, now I know the second equation going into it, and we did this the other day, is simply a cubic function with the right end up because I have a positive leading coefficient. Enter it in your calculator. you can see that I have it entered in my calculator. So what I need to do is I'm going to go down and I'm going to highlight that equal sign so it turns that equation on. I'm going to de-highlight my bottom two equations. So now I've only got the one graph turned on. I should still be in Zoom 6, so I'm not going to change it. So I think that I don't see the max of the graph very well. So I'm going to change my window. And I think if I just change my Y max to maybe 15, it should be okay. And that's not enough tick marks added that I really need to change my Y scale. So I want to remind you that if I want to trace, and I'm going to trace to the max, and I'm watching my cursor go to what looks like the tip top of that curve, but I'm also watching my Y values go 8.39, 9.28, 9.90, 10.22, 10.19. So 10.22 appears to be the highest Y coordinate I get to. Go to the left of that once or twice so that you've got a lower Y value. I'm going to go to my calculate menu. I want the max. Okay, so left bound, hit enter. Now right bound, arrow back to the right. Now 10.22 is what I thought was the highest, so arrow to the right of that a time or two to where you make sure that you've come down below 10.22. So right bound, hit enter. The guess just always enter on through. I'm getting that my max is at negative 0.823, comma 10.260 it looks like. Notice I'm rounding to 3 decimal places. 3 or 4 is fine. So I'm going to say that this max is at negative 0.823, comma 10.260. Leaving the 0 on the end indicates that I have rounded to 3 decimal places. Okay, let's go find our min. So I'm going to hit trace. I'm going to arrow, and I'm watching the cursor drop to the bottom of the curve, but when I get close, I start looking at my Y value. So my Y value is negative 7.5, negative 8.0, negative 8.25, negative 8.0. So negative 8.25 seems to be the lowest I can get to. So back off to the left of that to where I've got a higher Y value. Second trace. All right, I want the minimum this time. I am on my left side, so hit enter. Arrow to the right once, twice. No, negative 8.25 seemed to be my lowest, so go to the right of that so your Y values get higher again. And then I'm going to say right bound enter and guess enter. So I'm getting a minimum of 1.823, I think, and negative 8.260 again. So I'm going to go back and I'm going to answer that question. So 1.823, comma, and then negative 8.260. So just to reinforce what we did yesterday, I'm going to look at intervals over which the function increases, decreases, and is constant. So it's increasing, I see, on the first and the third pieces of the graph, so to speak. So when I go to say it's increasing, I'm going to say this graph is increasing on, remember I read it from left x to right x. So the first piece of the graph here, okay, goes from negative infinity to the x coordinate negative 0.823 union. Now the third piece of the graph right here goes from the x coordinate 1.823 to infinity. This guy is decreasing in the middle. So this middle portion is where it decreases. And so I'm going to say, well, the left x coordinate is negative 0.823. and the right x-coordinate is 1.823. And this thing is never constant. Most polynomial functions, I'd say all polynomial functions, won't have portions that are constant. Most functions in general won't have portions that are constant. Now, the big new thrust of today's lesson is to start recognizing families of functions and matching them with their equations and their graphs. So when I look at polynomial functions, I can have linear, quadratic, cubic, quartic, quintic, and higher. So of course, linear functions are pretty easy to recognize. So I know that lines are increasing or decreasing or horizontal. Now, I'm not going to write vertical because vertical lines would not be functions. They would fail the vertical line test. So a horizontal or a constant function is the horizontal line. All right. So constant functions would have the equation like y equals just some number a. All right. Of course, in general, you get diagonal lines, and general equations are y equals mx plus b form. All right. If I look at an identity function, I'll do this one in a different color to make it stand out. So an identity function is just the line y equals x, where you get 1, 1, 2, 2, 0, 0, -5, -5, and your x and y are identical. On that one in particular, when you draw your xy coordinate plane, if you've got 0, 0, 1, 1, 2, 2, and so forth and so on, that's the line with a slope of 1 that cuts through the first and third quadrants at a 45-degree angle. Now we know quadratic functions make parabolas. So you might have a parabola that opens up or a parabola that opens down. And of course I know that that would be in the form y equals ax squared plus bx plus c if it's in standard form. Remember, we're also familiar with vertex form and factored form for that matter. But you've learned parabolas in both of those forms. Now, cubic functions either go 1, 2, 3 or 1, 2, 3. So all the rest of these equations are going to kind of look the same. So I might have a cubic function that goes y equals ax to the third and then plus bx squared plus cx plus d. Of course, you could also have a cubic function in some sort of factored form. The same is true for quartics, quintics, and higher order functions. So quartics go 1, 2, 3, 4, general shape, or 1, 2, 3, 4. Now, I'm not making any inference about where the maxes and mins of the curve are. I'm just saying general shape, you're looking at w's or m's. And so you're looking for either y equals ax to the fourth plus bx to the third plus cx squared plus dx plus e for your equation. Or you would be looking for an equation that's in factored form, and you could count that the factors would add up to 4. Quintics are going to go 1, 2, 3, 4, 5, or 1, 2, 3, 4, 1, 2, 3, 4, 5. I about got carried away there. And that's totally not what I meant to do. I did the same thing twice. Goof. So I meant to say 1, 2, 3, 4, 5. There we go. All right, so quintics, of course, are y equals ax to the fifth power plus bx to the fourth plus cx to the third plus dx squared plus ex plus f. And it's a good thing I'm not going to list a bunch more of those. So any higher order polynomial doesn't have a special name, but we know they're going to lead off with like y equals an ax to the nth term. So if it's an nth degree polynomial function, and in general the next term would be some b times x to the n minus 1 where the exponent drops one time, all the way until you add on a constant term if there is one. So that's just a general look at polynomial functions. Now, rational functions are the ones that have fractions. So I'm going to give you some styles of equations, and I'm not necessarily saying the equations I give and the graphs I give go together. But your easiest, the easiest rational function would be your reciprocal function. And your reciprocal function is just going to be one that looks like this. And it winds up being basically a hyperbola with an axis of symmetry along the line y equals x. But the reciprocal function is just y equals 1 over x. Okay? That's your simplest fraction you could possibly have with an x on the bottom. But remember, you could have other functions like y equals x squared minus 4 over x cubed plus 1. That would be a polynomial or a rational function that's got a polynomial on the top and a polynomial on the bottom. You might have one that's in factored form, like I might say graph y equals x times x minus 5 over x plus 6 times 2x minus 1. So again, you would have a polynomial over a polynomial, which recreates a rational function. So remember, rational functions are those that you might have two vertical asymptotes, and it might be like this on the left end through the, my screen is not graphing where I mean for it to. It might have something that looks kind of like a cubic in the middle, and then something else on the right end. Remember, you can also have rational functions that perhaps just have one vertical asymptote, and then they might have some kind of a slant asymptote, and then they might have a piece here and a piece there. So rational functions sort of look like piecewise functions because they do appear in different pieces, but the pieces would only be separated by vertical asymptotes. Now, exponential functions come in two basic varieties. You could have an exponential growth function. Your simplest one would just be like y equals 2 to the x, or y equals e to the x. So again, I'm just giving you some basic equations. I'm not saying the equations necessarily go with the graphs. But you could also have an exponential decay function. And I want to remind you that I can move around these graphs. So what if I said, well, let's do exponential decay, but let's suppose that I move it down and to the right to where maybe my main point occurs not on the y-axis and the graph looks like this. So that would be exponential decay. So a decay graph is going to have a base, so I might say 5 times, but the base would have to be less than 1. Bases, though, in exponential functions are always positive, okay? You don't have negative bases. That's not an exponential function. That creates a completely different kind of graph. So you could have something like, another equation might be y equals negative 4 times 3 to the 2x plus 1 power plus 6. Those are all exponential functions where you see the x's in the exponents, okay? And you see the bases are e and then 1/2 and then 3. So your bases are always a positive number. Now on logarithmic functions, they're the functions that have a single vertical asymptote. So you might have something, and sometimes they call it the swimmer's curve because it looks like a swimmer taking kind of a stroke out of the water. Or you might have one that's been moved a little bit, and it might also, I tell you what, let's do this. You might have one that has been moved and flipped, for instance. So we might move that vertical asymptote to the left, and then you might have one that looks like this. Okay, so it kind of looks like a square root function, except square root functions just would stop at that fat point. Logarithmic functions keep going, but they're kind of the same shape. Not exactly, but kind of.
This is a test. 1, 2, 3.
So logarithmic functions are easy to spot because they have log or ln in the equation. So for instance, you might have 2 ln of 3x and then minus 1. So easy equations to recognize. Okay, so then we're going to look at the other types of functions. And remember, if you need to slow the video down, pause it, take your notes, and then resume, do that. The two radical functions that I want you to know are the square root and cube root functions. And then we'll talk about making sure that you know how to adjust their graphs. We'll talk more about that in the next chapter. But a square root function, of course, in its basic form starts at 0, 0. And then you have the square root of 1 is 1, so 1, 1's on the graph. The square root of 4 is 2, so 4, 2 is on the graph. I can also, though, remember, flip these graphs, spin them, move them right side up, upside down. So I could have one that I'm going to say, okay, I'm going to move it down 1, and I'm going to flip it to where it's upside down, and it shoots from right to left instead of shooting from left to right, that kind of thing. Now, we know that square root functions are going to have a square root in it, so it might just be as simple as square root of x, but you could have one that's got a transformation, like y equals negative 2 times the square root of negative x plus 5 minus 1. Square root functions are pretty easy to identify. Now, a cube root function, of course, its most basic graph is going to look like, sort of like a square root function. It says it's except you have the shape on both ends. And again, I could transform that. Like I might say I'm going to make it taller, I'm going to move it up, something like that. I'm going to flip it upside down so I could move it up, and then I could make it taller, stretch it top to bottom, something like that. But of course, your most basic one is y equals the cube root of x. But you could have transformations as well. So I might say, well, I'm going to make it taller, and I'm going to move it to the right, and I'm going to move it up. So I'm just showing you transformations in graphs, but keep in mind, I'm not making the equations match the graphs here. I'm just trying to get you to recognize, oh, that's a graph of a cube root function that's been transformed. Oh, that's a cube root equation. But I'm not necessarily matching graphs to equations. Now, you've not done...
This is a test. 1, 2, 3, 4.
I don't know if you can hear them making announcements in the background. Sorry about that. So with trigonometric functions, you can tell at this stage of the game because they're cyclical or repetitive, and we use the word periodic. So I'm just going to draw the x-axis. I'm not going to worry about the y-axis. But for instance, they're wavy like polynomial functions, but polynomial functions can be like up way high and down not so low and up again, and their ends point to the sky. But on trigonometric functions, you're going to go up and down and down and up and up and down and down and up. And what's going to happen is, I've not done a great job here, but every wave is going to have the same width and every wave is going to have the same height, and you're just going to keep repeating that pattern. And of course for you, I'm not going to say anything more than this, but trigonometric functions are going to have the words sine, cosine, tangent, or secant, cosecant, cotangent. We're not going to worry about those right now. We'll have a whole semester for that after the break and before the end of the course. But it might be like 2 times the cosine of pi x minus 3. So you look for the words sine, cosine, and tangent in those equations. Again, the equations are easy to spot. Now on piecewise functions, they're the ones that look like you've taken pieces of multiple graphs. So for instance, you might have a piecewise function where you have a line, for instance, for one part of the graph, and then you have maybe let me see if I can get that to graph where I want it to, a square root function for another piece of the graph. Or you could have one piece of the graph might be part polynomial, and I'll make that end with a closed or an open circle. One piece of the graph might be part constant, and one piece of the graph might be, I don't know, we'll say part quadratic. All right. So You can clearly identify the individual pieces of the graph as something we've already talked about. These don't tend to have vertical asymptotes. They could, but rational functions are separated. The pieces, it's all one equation, but the pieces are separated by vertical asymptotes. With piecewise functions, you have the functions that might look like this. And all of these, instead of y, I could have written f of x or g of x, etc., etc. But these are the ones where you have these pieces. And it might be that I say, you're going to do 2 to the x power if x is less than 1. You're going to make it x squared plus 6 if 1 is less than or equal to x is less than 2. And then you're going to do the square root of x if x is greater than or equal to 2. So those are the kinds of equations. And again, this equation doesn't match any graph that I just drew. But those are the piecewise functions. So the equations are easy to spot. Now, we're going to focus more on piecewise functions today. So we're going to work with our calculators. And I'm going to show you how to deal with your calculators. So you might say, well, wow, this is a lot. But guys, we're going to start with a general idea about piecewise functions. We're going to focus our work on a type of piecewise function, which is a step function. And then we're going to focus our work on step functions by doing a type of step function called a greatest integer function. So let's look at these functions here. Now the first thing we're going to do is just review evaluating piecewise functions. So if I want to evaluate, then I would say, let's see here, maybe I would say, let's evaluate f of negative 10. Well, when you do that, you say that negative 10 fits the first description of x. Negative 10 is an x value that's less than or equal to negative 1. Therefore, I plug into my first description of y. So I'm going to say, well, f of negative 10 then would be negative 5 times negative 10, which is 50. And 50 minus 4 is 46. Well, if I said, let's evaluate f of 7. Well, again, 7 is an x value that's greater than negative 1. So you're going to plug into the bottom description of y. So I would say, oh, well, 7 squared is 49. Make that negative. So negative 49 plus 5 is negative 44. So I just wanted to remind you how to evaluate piecewise functions. Now you can plot thousands of points and get a graph of a piecewise function, but let's be better than that. All right? So I make myself some hieroglyphics when I do this. So I know that the first piece of the graph, this one, is a line and it has a negative slope. So I know I need a piece of my graph that looks like that. Now I know the second piece of my function is an upside down parabola. So I need a piece of that parabola on my graph. Now here's the other thing I know. The first piece of the graph ends with negative 1 closed circle. So I'm going to remind myself, and that is not where I meant for that to graph or to mark on my screen. So I'm going to say, well, if I plug negative 1 into my first graph, I would have 5 minus 4 is 1. That's a closed circle. So I'm going to plot negative 1, 1, closed circle. Now, I can be more specific on my graph, but I'm not asking you to get too much precision. I know that that piece is the leftmost piece, and I already said it's a line with a negative slope. So if I wanted to do a good job, I would go up 5, left 1. But I don't want you to get too hung up. I just want you to go, oh, that line with a negative slope comes in from the left-hand side. It stops at a closed circle at negative 1, 1. Now, on the next piece of my graph, I need to do a couple of things, okay? Number 1, with a parabola, I don't know how much of the parabola I get. So I kind of start graphing the parabola, and then I'll figure out how to make it stop. So for instance, I know that my parabola, y equals negative x squared plus 5, goes up 5 and is upside down. Its a value is 1. So I'm going to go out 1, down 1 in both directions. So my parabola is going to do this, not where I was drawing. My parabola is going to do this kind of thing. Now, I know that this parabola goes from open circle -1, and I just said -1 squared is 1. Make it negative, so -1 plus 5 is 4. So I need to do something here. I need this thing to stop at -1, 4 on the left. Well, I've already got -1, 4 right there, but it's supposed to be open circle, so I need to go back and make it an open circle. So I'm going to use a little, there we go. I just sort of drew a hole in the point. All right. So let me show you how to do this on your calculator. So when you use your calculator, if you need your calculator for assistance, now for the most part, I don't want you to get calculator dependent, but I do want to show you that your calculator will do these. So let's go to our calculator and let me say y equals, and I'm going to come down and I'm going to turn this equation off. So I'm going to go back up. Now in y1 I want the leftmost piece of the graph. So I'm going to say, let me go ahead and enter that because I don't want it to be turned off. Well, I guess I'll get it in a minute. So I'm going to say parentheses -5x minus 4. So I put the regular equation in parentheses, and then I say parentheses, and it was supposed to be if x is less than or equal to -1. So I'm going to say x, okay, in the next set of parentheses. Now, I need to go to my test menu. So my test menu is above my math key. So I'm going to say second math. And it's supposed to be less than or equal to choice 6, -1. So that's telling my calculator only graph -5x minus 4 for this one condition. So now I'm going to go down. Now my next graph was y equals -x squared plus 5. So parentheses, -x squared plus 5, close parentheses, and then I'm going to say parentheses, x, and I got to go to my test menu, so second math key is greater than -1. So I'm going to zoom 6, and it'll graph. Now, what's interesting is that the calculator defaults to where it's got color on the x-axis. Ignore that. So your graph is showing you that you've got a blue line that corresponds to what we drew and a piece of the parabola in red which corresponds to what we drew. Ignore what's on the x-axis. That's just the calculator. That's the way it has to do it. But notice on this graph, it doesn't have open circles and closed circles or the arrows. So you're going to need to make sure that you come back, guys, and you fill in the arrow on the left side, the arrow on the right side, the closed circle on the left piece, and the open circle on the right piece of the graph. So you'll have to use your own judgment to fill those details in because I'm going to be checking for them. All right, so let's look at g of x. Let's start again by evaluating g of x. So if I said, well, can you evaluate maybe g of 1? Well, let's see here. 1 is an x value that would fall in this middle description of x. It falls between -2 and +2. So plot it here. So let's see, 1 cubed is 1, minus 1 is 0. Okay, got it. Well, could you evaluate g of 11? Well, let's see, 11 is an x value that falls in the third piece. So I'm going to plug it into my third value of y. So let's see, 11 minus 2 is 9. The square root of 9 is 3 times a -3 is a -9. Well, what if I said evaluate g of -2? Well, -2 falls on the first piece. It's a -2 is actually equal to -2. So I'm going to plug it into my first piece for y. So -2 plus 4 is 2. The absolute value is 2, but then I make it negative. So -2 plus 1 is -1. So that's just a review of how you evaluate. Now let's graph. So again, guys, I'm going to look at my first piece. Okay? I know my first piece is an upside down V shape. All right, now I'm going to use transformations. The x plus 4 tells me my v shape goes left 4 and up 1. Okay? I know it's going to go have a slope of -1, so out 1, down 1. So my V shape kind of looks like this. Now, how far does it go? Well, it's supposed to stop at -2, closed circle. So again, I've already done -2. I got -2, -1. So let me plot -2, -1 on my graph, closed circle, and that ends the V-shaped part of the graph. So now in the middle, I'm going to have to do some work here. So this part, y equals x cubed minus x, I know the basic shape is this kind of thing, but I need to know kind of where to put it, so I'm going to use my skills from Algebra 2. So I'm going to say x times x squared minus 1, so that's x plus 1, x minus 1. Well, guys, that tells me it has roots at 0, 1, and -1. So I'm going to plot those points, and let's see here. It actually starts at an open circle of -2. Let's see here. -2 cubed is -8, minus a -2, minus a -2 is +2, so -8 plus 2 is -6. So it starts at -2, -6. That would be down here. It ends at an open circle at +2, which would be 8 minus 2 is 6. So it ends at 2, 6. I don't think I'm going to get any awards for how well spaced, and that's not where I put that, how well spaced my y-axis is. So guys, now I'm going to piece it together, and I'm going to say, okay, from the open circle it goes up through a root, down through a root, up through a root, and back up. Now, I don't know how high the max and min is. I didn't judge that. I'm just getting a basic graph, guys. It's not going to be perfect totally because I'm not doing that much analysis. Now, on my last piece of the graph, okay, I know that this piece is a square root function that's upside down. So I know the basic shape of this guy looks like this, okay? I can tell that it goes right to. So if it goes right to, it's going to start right there, okay? And I can see that it starts at closed circle 2, comma. Well, since 2 minus 2 is 0, the square root of 0 is 0 times -3 is 0, it actually starts there. And you know what? I'm not going to do any more thinking about it. I'm just going to make the basic shape and be done. Okay? Let's do this one on the calculator, and we'll take a little break. So what I'm going to have to do on this one is show you how to punch this in your calculator. I'm getting myself set up and ready to go. And you may be going ahead and punching some things in on your calculator. You might be asking, what are you doing? I'm writing the equation down so I can see it when I change screens. Okay, here we go. Sorry for the little bit of a delay. So y equals, let me just clear these out. All right, so my first piece of the graph is the negative absolute value. So I need to go negative. And then if I go to my math menu, I'll find my num menu, and I'll go to the absolute value option. So there's my absolute value bars. X plus 4 goes in there. Let me arrow to the right so I jump out of the absolute value bars and say plus 1. So that ends my equation. Now I'm going to say parentheses, x is, and I need to write in less than or equal to, so test menu, second math, less than or equal to is 6, and then -2, close parentheses. Now in the middle, I need to say y equals x cubed minus x, so x to the third minus x, close parentheses. Now, here's what you need to know on this. You can write in -2 is less than x is less than 2, but your calculator won't read it. So change it to two separate inequalities. So one of them is going to be that x is greater than -2. So test menu, x is greater than -2. So that's one condition. And then a second condition is that x is test menu less than choice 5 +2. So you need to know that your calculator will not accept both of those together. You can punch it in, but your calculator will not read it or graph it right. So just FYI. Now my third equation is -3. Make sure you're using your negative key, not your minus key. 3 times the square root of. So I'm going to say second square root. Here I've got x minus 2. Arrow to the right so you jump out of the square root symbol so you can close up the parentheses there. And then x is greater than, so new parentheses, x key, test menu, greater than or equal to 2. And when you enter, then you ought to be able to graph that. So again, ignore the red and blue marks on the x-axis, but do you see your V-shaped graph, then your cubic-shaped graph, and then your square root-shaped graph? And you should go, yeah, that looks like ours, but you are responsible, once again, for adding arrows on the far left end and the far right end, for adding your closed circle, open, open, and closed circles. We're going to pause there and then we'll pick up with our next video.